class. Back to linear algebra. In the last lesson, we introduced the idea of a linear transformation. We now have the definition and a few examples. Now let's go through the properties of linear transformations. So say we've got, in our setup, V and W are vector spaces, and L goes from V to W is our linear transformation. Here's a claim. Claim 28. 1. Say we've got the zero vector in V. L applied to the zero vector in V is equal to the zero vector in W. A linear transformation sends zero vectors to zero vectors. Let's prove this. Say we look at the left-hand side of this equality and try and figure out how to get to the right-hand side. Well, if you recall, the zero vector in any vector space is equal to 0, the scalar, times some vector for some vector in the vector space. Linear transformations are linear, as in you can take out a scalar. This is by the definition of linear transformations. And again, since here we have an element of the vector space W, 0 times that element is going to be the zero vector in W. QED, end of proof. Claim 28, part 2. L applied to the additive inverse of a vector is equal to negative, as in the additive inverse of L applied to the vector for all vectors in V. Here's an exercise for you. Establish claim 28, part 2. It follows very similarly to part 1. Claim 28, part 3. L applied to this linear combination, alpha 1, V1, plus all the way up to alpha n, Vn, is, as you would expect, a linear combination of the linear transformation applied to the individual vectors. And this is for the alpha I, real numbers, and the V's are vectors in the vector space. The definition of linear transformations technically only tells you how to apply L to a linear combination of two vectors. This is a linear combination of n vectors where n can be larger than 2. The proof, as you might guess, is going to be by induction on n specifically. The base case, n is equal to 1. Well, this is what we would have. We know that this is equal to alpha 1 L applied to V1 by the definition of linear transformations. We're going to assume this works up to n is equal to k, and then we'll do our induction step. The n is equal to k plus 1 step. Well, we're going to apply L to alpha 1 V1 through alpha k Vk plus alpha k plus 1 Vk. The definition of linear transformation says that we can apply our rules for linear transformations directly to the sum of two vectors. So we're going to break this up into two vectors, like so. This is going to be L applied to the first part of this linear combination plus L applied to the second. This is by the definition of linear transformations. And then we're going to use induction. Here we've got k, and we've assumed that this k different vectors, and we've assumed it works up to k different vectors. So we've got alpha 1 L v1 plus dot 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 alpha k L vk, and on the right we've got alpha k plus 1 L vk. This is by the induction hypothesis. And that's our proof. We got what we needed. QED. Okay. Here's what we've shown. Claim 28. 1. A linear transformation sends 0 vectors to 0 vectors. 2. A linear transformation sends an additive inverse to the additive inverse of the linear transformation applied to that vector. And 3. The linear transformation acts as you would expect it to on a linear combination of vectors. Plus alpha n L Vn. This is what we know. Having a linear transformation actually also gives us access to new subspaces. Here's a definition for you. Say L from V to W is a linear transformation. The kernel of L is denoted ker. It's defined to be all the vectors in the vector space such that L applied to V is the 0 vector in the W vector space. Note, if this feels a little bit familiar, it's because it should feel familiar. The kernel is the generalization of the idea of a null space. So when L is represented by left multiplication by a matrix A, then the kernel of L is just the null space of A. Let's do an example. Example, say L is a linear transformation from R2 to R2 that sends a vector x1, x2 to x1, 0. This will be represented by a matrix. This matrix looks like so. The kernel of L, well, it's all the things that get sent to 0, which means that x1 has to be 0. This is going to be all the things of this form, 0, x2. Where x2, of course, is some real number. This is otherwise known as the span of E2, where, remember, E2 is the vector 0, 1. Here's an exercise for you. Say D is differentiation. It goes from the differentiable functions on the interval AB to the continuous real valued functions on the interval AB. And it sends f to f prime, differentiation. The question for you is, what is the kernel of this linear transformation? There are also other subspaces associated to the linear transformation L. Definition. Say L is, of course, a linear transformation from vector space V to vector space W, and S in V is a subspace. Then we say the image of S under this linear transformation is denoted LS. it's defined to be all the vectors W in the vector space W such that W is L applied to some vector in S. It's all the things hit by vectors in S using the linear transformation. The range of S is LV. It's the collection of vectors in L applied to all of the vectors in V. Okay, let's do an example. Example, say L is a linear transformation R2 to R2. It's the same one that we did before. X1, X2 gets sent to X1, 0. Say S is the subspace that looks like so, 2x2, x2, where x2, of course, is some real number. Said otherwise, this is the span of the vector 2, 1. Then LS, well, what are all the things that it goes to? It's going to be A0, where A is some real number, otherwise known as the span of, well, the span of L of 2, 1. And what's L of 2, 1? This is the span of 2, 0, which is just the span of E1. All right. Exercise for you. Say L is the linear transformation from R3 to R squared. This is represented by a 2 by 3 matrix, 1, 1, 0, 0, 1, 1. And here's what it does. It sends x1, x2, x3, the vector, to x1 plus x2, x2 plus x3. Say S is going to be the span of E1, E3, where recall E1 is 1, 0, 0, and E3 is 0, 0, 1. What is the image of S? And what is the image of R3? All right. Claim. Claim 29. As I've been saying before, say L from V to W is a linear transformation. We claim that the kernel of L is a subspace of V, and we claim that the image of S is a subspace of W when S is a subspace of V. Let's talk a little bit about this proof. Proof that the kernel of L in V is a subspace. Well, to be a subspace, you have to be non-empty, closed under addition, and closed under scalar multiplication. So say we've got X and Y in the kernel of L, and say we've got alpha in R. Well, we know that L of the 0 vector is equal to the 0 vector in W. This means that the 0 vector in V is in the kernel of L, and the kernel of L is non-empty. Let's take L applied to the sum of x and y. Well, because of the definition of linear transformations, this is just L of x and L of y. They're taken from the kernel, so this is the 0 vector in W plus the 0 vector in W, which is the 0 vector in W. So x plus y is in the kernel of L. Last but not least, L applied to alpha times the vector x. By the definition of linear transformations is alpha times L of x. X was taken from the kernel, so this alpha times the 0 vector, and the 0 vector times any scalar is, again, the 0 vector in W. And this means that alpha x is in the kernel of L. And putting this all together, the kernel of L is a subspace. QED. End of proof. Here's an exercise for you. Prove that the image of S for some subspace in S and V is a subspace of W. As I said, for some subspace, for any subspace, S in V. All right, we've now done the properties of linear transformations. Think on this. Talk to you next time.